One of the most common operations carried out in a lab is the process of dilution, in which more solvent is added to a solution in order to produce a less concentrated solution. We can solve dilution calculations to figure out new concentrations or the amount of a solution that we need by using dimensional analysis, or we can use the simple relationship here, C1 times V1 equals C2 times V2, where the C stands for concentration, usually molarity, although the other concentration terms will work, and the V terms stand for volume. You'll notice that this is similar in structure to Boyle's law, which we saw in the previous chapter. For example, let's say that we have a solution here which has blue food coloring in it. What we see is that the solute particles, the food coloring, are relatively close to one another, and there's water molecules in between, although we don't have actually see them in this drawing. When we add solvent, you'll notice that the color becomes a little bit more pale. The process of adding the water is called diluting. And you will notice the effect that there are fewer solute particles in a given amount of volume. So it's very critical to know that a dilution always lowers the concentration. Concentration must go down as we add more solvent. So let's take a look at an example here. So chemical stockrooms will typically have on hand what they call stock solutions, which are solutions that they've made and which they will dilute in order to make less concentrated solutions for whatever need they might have. So let's say that we have a 6 molar stock solution of sodium hydroxide, and the chemical stock person would like to make 10 liters of a much less concentrated solution, a 0.15 molar solution. So what we would like to know is what volume of the original stock solution is required. Let's go ahead and go to our notes view and solve this problem. We want to approach this problem in a way similar to what we did with the gas laws. First, we're going to identify each variable. Here, the 6.00 molar solution is the starting concentration, so I label that as C1. The 10 liters is the final volume, because it says that's what I would like to prepare. And the concentration of the final solution is C2. So here is our equation for dilution. The starting concentration times the starting volume equals the ending concentration times the ending volume, where the unknown that we would like to find is the starting volume. So let's solve for the starting volume by dividing both sides by the starting concentration, C1. This gives us the rewritten form of the equation, C2 times V2 divided by C1 equals the starting volume. Now, all we have to do is substitute in the values that we labeled. So, as we saw earlier, the starting concentration is 0.15 molar. And I'm going to go ahead and write out all the units here, moles per liter. The final volume is 10 liters. And the starting concentration is 6 moles of sodium hydroxide per liter of solution. Now that I look at this, I see I didn't really need to write out the full expression for molarity. And so the molarity terms cancel out and leaves liters as the only unit. And putting this in the calculator gives a starting volume of 0.25 liters. It's two significant digits because the value of C2, 0.15, is only two significant digits. And so what we would do is take a quarter of a liter, 0.25 liters, which would be equivalent to 250 milliliters of the stock solution, and then from there we dilute it down to a final volume of 10 liters. When a solute is added into a solvent, we observe that the solute would gradually spread itself out over time from a region where it has high concentration, meaning where it was initially added, to an area of lower concentration where it is uniform throughout the entire container. For example, let's say that we add a drop of food coloring into water. When it first hits the surface of the water, particularly if the water is very cold, what we will see is that the drop mostly stays together. And then you'll see the drop starts to get pulled lower and lower in the solution, and it seems to form ribbons as it slowly spreads out. Given more time, and especially if we stir the solution, the solute will spread out completely through the solvent. And by the end of this diffusion process, we would expect that the concentration of the solute should be entirely the same at every region throughout the solution. The only idea behind stirring is that we want to make the process go a little bit faster. But in theory, given enough time, a solute will completely diffuse. A closely related topic is osmosis, and we're going to specifically look at what is called the osmotic pressure. So let's say that we take two solutions and they have the same solute in them. It's not required, but it'll be easier if we think about it that way. And these solutions have unequal concentration. So say one side is 1 molar and the other side might be 2 molar. And so they're separated by what we call a semi-permeable membrane. A semi-permeable membrane is a barrier that only allows certain chemicals through it. It's a very selective wall. And for now, let's just imagine that the only thing that can go through this membrane is water. So in this kind of a scenario, when we have these two solutions separated from each other by this semi-permeable membrane, water will flow across both sides. However, it will tend to flow more from the less concentrated solution towards the more concentrated solution to ultimately equalize the two. It might not be able to equalize the two, but the flow will continue. And this is a process that we call osmosis. And again, the solvent goes from the less concentrated region towards the more concentrated region of solute. Incidentally, we could also look at this from a different perspective and say that the water is flowing from an area of high concentration to an area of low concentration. Because the idea here is that if we have water in a less concentrated solution, the more concentrated solution has more solute, less solvent. So the water is trying to go in that direction to dilute the more concentrated solution, to spread out its own concentration. But it's easiest to remember as simply solvent follows solute, or water follows solute. Now, as the water is flowing from the side of lower concentration towards the side of higher concentration, suppose we wanted to stop this from occurring. We would have to put a pressure on the solution, and we call that the osmotic pressure. So it's the amount of pressure you need to apply to stop the process. So in general, the greater the difference in the concentration of the solutes in the solution, the greater the osmotic pressure. Now, what's tricky about osmotic pressure is it's not always just a matter of looking at the concentration of the solutes. It's the concentration of the solute particles. And let's see if we can kind of explain that here. So let's say, for example, we take 1 mole of sodium chloride and we dissolve it in solution. 1 mole of sodium chloride actually gives you 2 moles of particles. Sodium chloride is a soluble ionic compound. It's a strong electrolyte, so it completely dissociates into ions. So that 1 mole of sodium chloride gives you 1 mole of sodium ions and 1 mole of chloride ions. So if this were in a liter, this wouldn't be a 1 molar solution. It would actually be a 2 molar solution from the perspective of ions, how many ions there are. Let's say, on the other hand, we took a mole of iron 3 chloride and we dissolved it. Well, if this completely dissociates, it will actually form 4 moles of particles, because we would expect we would get 1 iron 3 ion, and then all 3 of those chloride ions would separate for a total of 4 moles of particles for every 1 mole of iron 3 chloride. This would be an ideal situation. Whether in fact it actually goes to 4 moles or whether some of those chlorides want to stay behind is a difficult question to answer, but we're going to just assume that all of these ions completely dissociate. So given this, we want to be able to rank these solutions in order from the highest osmotic pressure to the lowest. So what we're going to look at here is what has the highest concentration of ions. That's going to be the one with the highest osmotic pressure. So we have to understand the nature of each of these solutes to predict how this is going to work out. So let's go ahead then and take a look at the first solution. So we have magnesium chloride here. This is 0.20 molar, so it looks like it's the least concentrated of the 3. But magnesium chloride, aqueous. So when we put this in water, it's really a magnesium ion and 2 chloride ions. So that's 1, 2, 3. It gives us 3 particles for every 1 mole that dissolves. So the true molarity of the ions is actually 3 times the starting molarity. So it's 0.20 molar times 3. So it's 0.60 molar. Sodium chloride, on the other hand, when it dissociates, it gives us 1 sodium ion and 1 chloride ion, for a total of 2 ions for every 1 mole of sodium chloride. So that means that the true molarity is going to be 0.25 molar times 2, or 0.50 molar. How about glucose? Glucose is a non-electrolyte. It's not an ionic compound. We can tell by the fact that it's all nonmetal atoms here. That usually will work. So if it's a non-electrolyte, that means nothing dissociates, and the true molarity is just the given molarity. So it is 0.30 molar. So just looking at these numbers, you might have assumed that C, being the most concentrated, has the highest osmotic pressure. But when we look at the true, real molarity of particles, we see that actually A has the highest concentration. It's 0.6. And then B is the next most concentrated, while C is actually the least concentrated in particles. So if we were to rank these in highest osmotic pressure to lowest, A has the highest pressure, then B, and then finally C. Osmosis is a critically important process in biological molecules, particularly with red blood cells. So if we look at some of our cells, their shape, their structure, can depend on the concentration of the particles in which they are surrounded. And so we'll go ahead and limit ourselves to red blood cells, which have kind of a disc-like shape to them. And that disc-like shape is very important for them to successfully flow through blood vessels all the way down to the capillaries. So if we were to look at the fluid of a red blood cell environment, it typically has a concentration of sodium chloride equivalent to 0.9%. Now, this would be kind of an exaggeration. This is assuming that the only solute in the red blood cell is sodium chloride. It's a much more tricky situation than that. But just to keep things easy, we're just going to say that the only thing we have to worry about right now is that number of 0.9% for the sodium chloride. Any solution in which the concentration is equivalent to that would be considered isotonic to the cell. So what we would expect, looking at osmosis, is that if a solution has the same concentration outside of the cell as inside the cell, water should flow into the cell at the same rate that it's flowing out of the cell, and so there's no real change to the shape or volume of the cell. So suppose that instead that the cell is placed in a solution with a sodium chloride solution concentration of 1.50%. So the outside of the cell has a higher concentration than the inside of the cell, which we said was 0.9. We say that the concentration of that solution is hypertonic relative to the cell. So if the solution outside is higher concentration, it's hypertonic solution. And so what we would expect then is, because of osmosis, the water is going to flow towards the more concentrated region. So it will flow out of the cell more rapidly than it enters. So as water flows out of the cell will start to shrink and it will start to deform its shape. And we call that process crenation. If we take a look at a visual sample of what's happening to blood cells in a hypertonic solution, so these are our blood cells, and this right here is the hypertonic solution. The water is flowing out of the cells more rapidly than it can flow in. You see it tends to take on kind of a spiky shape. Over here in particular, we see that the shape is kind of deformed. It almost looks like a leaf cookie cutter or something strange like that. So this will certainly have an impact on the way that these cells might flow through blood cells. On the other hand, let's say that we place cells in a solution with a much lower sodium chloride solution than what's inside the cell. So again, one more time, inside the cell we're saying is 0.9%. If this is 0.1%, that's much, much lower. We call such a solution a hypotonic solution. So more is hyper, less is hypo. So a less concentrated solution is hypotonic relative to the cell. So which way is the water going to go? It's going to go from the lower concentration solution to the higher. And I think you can see that that will be a bit of a disaster, because water will start to flow into the cell much more rapidly than it leaves. And these cells can only expand in size so much. So we would expect the cell to expand, and if the process continues indefinitely, the cell will burst. We call that hemolysis. Hemo for blood and lyse for break. So the blood cell is breaking open. This is why we never want to give someone an IV solution that is pure water. Doing so can ultimately be fatal because it could induce some of the cells to undergo hemolysis, because water would always be hypotonic relative to a blood cell. This is the end of Chapter 7 on solutions. In the next chapter, we're going to look a little bit further at solutions, specifically at the properties of acidity and basicity, which are very important for biological systems. Thank you.